pre-tensioning as well as post-tensioning. Now coming to here, once again we have seen that there are another types of losses are there. These losses are, we are calling them as instantaneous losses as well as time dependent losses. So we have seen that there are two types of losses are there. So one is instantaneous loss, another one is time dependent loss. So in the instantaneous losses, we have seen that loss due to elastic shortening, so this elastic shortening, we have written a formula that is M into Fc. So if you observe loss in pre-stress due to elastic shortening of concrete, that is the formula is M into Fc. So where M is nothing but modular ratio, so this is ES by EC we have written, and Fc is equal to, that is stress in concrete at level of steel, stress in concrete at the level of steel, which is equal to, we have written the formula P by A plus P into E square by I. So this is M is equal to ES by EC, that is E is nothing but, if nothing is given, you can assume it as a 210 kilonewton per mm square or 2.1 into 10 power 5 Newton per mm square. Whereas EC is nothing but 5000 root FCK. We know this one as per our IS 1343 2012, the grade of concrete, if it is known, you can assume this as 5000 root FCK. So that is Young's modulus of concrete. Whereas this is steel, if that is not given, you can take it as 2.1 into 10 power 5, or sometimes 2 into 10 power 5 will also be assumed. So I think in the caudal provision it is given as 2 into 10 power 5 Newton per mm square, that will be assumed. So with this formula, we can calculate what is the loss due to elastic shortening in pre-stressing steel. So this loss due to elastic shortening in pre-stressing steel, now we can calculate for pre-tensioning as well as post-tensioning. We have already discussed this. Pre-tensioning as well as post-tensioning. So what is happening? In case of pre-tensioning, the value will be M into Fc. But in case of post-tensioning, it is observed that this value will be 0 when all the wires are pre-stressed. When all the wires are pre-stressed at a time. So when all the wires are pre-stressed at a time, then the loss due to elastic shortening is 0. That means you are having 3 cables. These 3 cables, they are stressed at one time. So 3 wires, they got stressed at one time. Then loss due to elastic shortening will be considered as 0. Loss due to elastic shortening will be considered as 0. Whereas coming to the next one, in the second case, one cable is stressed free one by one. That means we call them as successive tensioning. So when we are doing this one by one, then what happens is when first wire is stressed, there will be no loss. But when the second wire is stressed and locked or anchored, this second wire will give a loss of stress in the first wire. When the third wire is stressed, this will give a loss of pre-stress in second and first wires. Just once again, I am repeating, understand this concept. So simply we can't do M into Fc. We can't simply consider M into Fc. It is very, very important. So compulsory you will get this question in second unit. So the loss of pre-stress due to elastic shortening. So this loss of pre-stress will be considered in 2 considerations. So one point is when all the wires are stressed at a time, then the loss of pre-stress is 0. But when you are stretching the wires one by one, So first wire is stretched and locked. Second wire is stretched and locked. Third wire is stretched and locked. Then what happens is, first wire when you are stretching, so there is no another, that means in front, before this first wire, no another wire is stretched. So that's why it is not creating any loss of pre-stress and the before predecessor wires. So now in this one, when second wire is stretched, or second tendon, steel wire or tendon or rod, whatever the bar, when it is stretched, this will give a loss of pre-stress in the first wire. When the third one is stretched, it will create the loss of pre-stress in second and first steel wires. So that is here we have to understand. Now to solve them, before going to the further losses of pre-stress, we will solve some of the problems. We will understand this concept, then we will move further one by one. All the 6 losses, for every loss, after writing down the formulae, we'll understand the concept, we'll solve some problems, then we will move forward for calculating the total losses of a given beam later on. So you can note down the problem. I'm just erasing this part. You can note down the problem. So I'm writing down the question. A pre-stressed concrete beam of rectangular section (150 mm) wide and 300 mm deep is pre-stressed by eight high tensile wires of 7 mm diameter located at 100 mm from the soffit of the beam. Soffit, the meaning is nothing but bottom. From the soffit of the beam. If the wires are stressed to a stress of 1100 Newton per mm square, calculate the percentage loss of stress due to elastic deformation assuming Young's modulus of concrete is equal to 31.5 into 10 cube Newton per mm square. ES is equal to 210 into 10 cube Newton per mm square. All of you make a habit to note down the question and maintaining the running notes. We are at the middle of the second unit. So at this stage, you people should not just simply listen the class. Now coming to this, so write down the given data. So with the given values, first of all, write down the given data. So what is that value here? First of all, area of the cross section B is given, which is 150 mm wide. D is given 300 mm. You can note it as capital D only. Here the clear cover term will not be there. D is equal to 300 mm. So it is said that it is pre-stressed by 8 high tensile voids of 7 mm diameter. So tensile area of pre-stressing steel, write down. Area of pre-stressing steel AP is equal to, so 8 diameter 8 into 5 by 4 multiplied with 7 square. Area of cross section A is equal to 150 into 300. Then area of cross section is calculated. Then second moment of area or moment of inertia. Second moment of area BD cube by 12. Now tell me this value. 150 into 300 cube by 12. So now here I know that this is the area of pre-stressing steel, and initial pre-stress applied is given. So initial pre-stress, if you observe the question, the wires are stressed to a stress of, so initial stress FPI is equal to 1100 Newton per mm square. Initial pre-stress is 1100 Newton per mm square. So with this value, with 1100 Newton per mm square, we can write down the pre-stressing force. So write down pre-stressing force is equal to, so simply AP multiplied with FPI, area of pre-stressing steel, multiplied with the initial pre-stress. So this is called as a pre-stressing force. After writing the pre-stressing force, now I need to calculate. So what they are asking, calculate the loss of pre-stress. We will also calculate here what of here first of all our beam is pre-tensioned, so that's why when the beam is pre-tensioned, you need not bother whether it is the successive or at all the wires are stressed at a time or one by one, then you need not bother about it. Why? Because here in this this is a pre-stressed, actually you make it a note of, this is pre-tensioned, just to make a note of this. This is pre-tensioned concrete beam actually. So pre-tensioned concrete beam, that means when all the wires are stretched at a time or one by one, I am not having any problem with that. So when we are not having any problem, we'll move further. So now in this, so pre-stressing force P is equal to AP into FPI. Now calculating the next step, modular ratio. Yeah, in some other textbooks they are writing it as alpha E, whatever the term, just we are following our comfortable terminology, that's it. So this is ES by EC. So this is 210 into 210 into 10 cube, 31.5 into 10 cube. Modular ratio M is equal to 6.67. Now we need to write down the stress in concrete at level of steel, FC. Stress in concrete at level of steel, that is nothing but FC is equal to, I'm calculating the stress in concrete at level of steel, FC is equal to, so we know what is the formula here, what it is given. Just see this, this is your cross section of the beam. You can also make a note of this. So this is the cross section of the beam, this is the neutral axis. So in this neutral axis, the depth is given as 300 mm, width is given as 150 mm. So when depth is 300, width is 150, now it is said that you are pre-stressing 7 mm diameter 8 wise, they are placed at 100 mm from the soffit of the beam. So soffit, this is called as soffit. The portion which is there, the bottom, this is called as soffit of the beam. So from the soffit, the wires are placed. So these 8 number of wires, they are placed like this. So from here to here, it is given as 100 mm. If this is 100, you know that the entire value from here to here, it is 150 mm. So you can consider this as 50 mm. So this 50 is nothing but eccentricity E. So eccentricity E is equal to 50 mm. Now understand, when you are calculating the stress in concrete at level of steel, at this level you are calculating. So when you are calculating stress in concrete at this level, that is below the neutral axis, you will write down the formula as plus P by A plus P into E square by I. So here E is 50 mm, P value is, you have already calculated, what is that value? Area of the cross section is 45,000 plus 338.65 into 10 cube into 50 square by moment of inertia 337.5 into 10 power 6. Tell me the value of FC, which is in terms of stress, which is Newton per mm square or MPa. So this is stress in concrete at level of steel. We need to calculate the loss of pre-stress in steel. So you write down loss of stress in steel due to elastic deformation is equal to M into FC. So this is M is nothing but you have already written 6.67, which is obtained from here, into 10.02. We will write down percentage loss here. Percentage loss of stress due to elastic deformation is equal to, you know, this is the loss. So loss by initial stress into 100. Percentage loss of stress due to elastic deformation is equal to loss, which is 66.90 by initial stress 1100 into 100. Now with this, now first of all write down the given data. Write down the given data. So what is the first one? First of all, the beam width is given, B is equal to 200 mm. D is equal to 300 mm. Initial pre-stress is equal to 840 Newton per mm square. Area of pre-stressing steel, API. AP, it need not be API, you have to write an AP. Area of pre-stressing steel. So in this area of pre-stressing steel, just see this. How many total number of voids are there? See the cross section of the beam. When you observe the cross section of the beam, it is said that, so this is your beam. In this, the neutral axis is there. This is 200. This is 300. Now, just go to the problem and check it. 15 number of wires of 5 mm diameter are located 65 mm from the bottom of the beam. So 65 mm from the bottom of the beam, the numbers are 15. So from here, if you observe here, there are 15 number of wires are there. Like this. So from where to where, here this distance is 65 mm. So 65 mm from the bottom of the beam, they are located. Now the next is, just tell me what is this distance. Can any one of you tell me what is this distance? Eccentricity from the neutral axis?
85 mm.
85 mm. So total is 150. 150 minus 65. So this is 85 mm. So the eccentricity for this 15 wires is 85 mm. Now see, continuation of this, along with these 15 wires, the wires are located, 3 wires are located at a distance of 25 mm from the top of the beam. So 3 wires are located at a distance of 25 mm from the top of the beam. So this is 25. So if this is 25, you know what is this value? What is this eccentricity?
125.
125.
So you can take it as this is 125 mm. Okay, so here we need to calculate the stress in concrete at level of steel at this level, as well as the stress in concrete at level of steel at this level. So we need to calculate for both the cases. Why? Because here it is different. Now, coming to this, or otherwise we will do one thing. Here, what is the area? Okay, come back here. So this is how the tendons are located, or the wires are located in the pre-stressed concrete beam. So we need to first of all calculate, here 15 wires are there, here 3 wires are there. We need to calculate what is the centroid or center of gravity of these wires. Centroid of these wires is to be calculated. So before calculating that, here AP is given as area of pre-stressing steel is 18 bars are there, each bar of 5 mm diameter. So what is this value? Now, the pre-stressing force P is equal to AP into FPI. So 353.42 into 840. What is the value? So if this is calculated, now after that we need to see what is the centroid of the, or the position of centroid. So just write down position of centroid. Position of centroid of the wires from the soffit of the beam. Soffit of the beam means I would like to calculate from here what is the centroid of this. So I can see that if you remember, I can write down this one as assume it as something like y1, and from here to here you assume it as y2, and here this is you assume it as a2, and this 15 by assume it as a1. So from the soffit of the beam you are calculating, so you will get it as what is the position y bar. Y bar is nothing but, so from the soffit of the beam you are calculating, so y bar is equal to a1 y1 plus a2 y2 by a1 plus a2. So a1 is 15 number of bars are there, which of pi by 4 into 5 square plus, sorry, into, so this is 15 number of bars. What is y1 value here? So this is a1. So what is the value of y1?
65.
So y1 is 65 plus a2. So there are 3 number of bars are there. So just this is 3 into pi by 4 into 5 square into, now tell me what is this distance, y2 distance?
275.
275. So how you got that one? Y2 is nothing but from the top of that total is 300 minus 25 from the top. So from the soffit of the beam we are calculating. So that's why this is 275 by a1 plus a2. a1 is 15 into pi by 4 into 5 square plus 3 into pi by 4 into 5 square. Now tell me what is the y bar distance? What is the y bar distance? That means from the soffit of the beam, the distance is 100 mm. So if this is 100, you know that this entire distance is, what is this one? 150. So this eccentricity is nothing but now eccentricity E is equal to 150 minus 100. 50 mm. So eccentricity E is equal to 50 mm. So this is below the neutral axis. Now write down stress in concrete at level of steel. Stress in concrete at level of steel. So stress in concrete at level of steel, what is the formula? Plus P by A plus PE squared by I. Substitute the values here. Plus P by A plus P into E into, so this is, we are writing it as FC. So FC is equal to P value, capital P. How much you got? 296.88 into 10 cube by area of the cross section. Have we calculated these values or not? I think if you don't calculate,
No, sir.
yeah, no problem, no problem. You can write down here A is nothing but area of the cross section. So what is the area of the cross section? 200 into 300 directly. So this is 296.88 into 10 cube. So what is the eccentricity? 50 square by area, moment of inertia, 200 into 300 cube by 12. So you can substitute here and tell me what is the stress in concrete at level of steel. So 6.59 Newton per mm square is obtained. Now we need to calculate loss of stress in steel. Due to elastic shortening or elastic deformation, both are the same. So what we are writing this as M into Fc, where M is nothing but ES by EC into Fc. ES is 210 kilonewton per meter cube per mm square. This is EC is 31.5 into 6.59. So tell me what is the loss of stress you got here?
49.93.
49.93.
43.93, sir.
Okay. So this is the percentage loss due to elastic deformation. Percentage loss due to elastic deformation. Till now, whatever we have done, this is regarding pre-tensioning cases. Pre-tensioning cases, that means all the wires they got stressed at a time or when they are stretching one by one. In the case of pre-tensioning, there is no problem. Why? Because in the case of pre-tensioning, what is happening, just understand the concept of pre-tensioning. In case of pre-tensioning, your wires are stretched one by one, whatever the wires are there, then you pour the concrete. So at the time of release, so they will create one by one. That means stretching of the wires will not create any effect on the surrounding concrete. Why? Because the stretching is completed already. Now, whereas coming to post-tensioning, what is happening? Your concrete is there, and after that, inside you are providing a duct. So when you are providing a duct inside, now, for example, something like you will provide a duct like this. So if you want to provide a straight tendon, you will provide a straight duct. So now the tendon will be placed here like this. Now this is stretched, first cable is stretched. When the first cable is stretched, due to this, it may give the loss in the, that means when the second cable is stretched, so this may give the loss in the first cable. So when all the wires are stretched at a time, then there is no loss, but when they are doing one by one, then they will create certain effect on the members. So we will see that now. Go to the next problem. Here what I am doing is I am explaining all the different types of case problems, different case problems in this loss due to elastic shortening. Similarly, different types of problems will solve for each loss. Then they are asking you to calculate the total losses for the given beam according to the given data. Using this, each type of losses, we can calculate the entire losses later on. Now go back to this problem, a post-tensioned concrete beam. A post-tensioned concrete beam (100 mm wide and 300 mm deep is pre-stressed by 3 cables. by 3 cables, each with a cross-sectional area of 50 mm square and with an initial stress of 1200 Newton per mm square. All the cables are straight. And located at 100 mm soft from the soffit of the beam. If the modular ratio is 6, calculate. Hariprasad, roll number 128. Are you there in the class? Hariprasad. Roll number 143, Rajita.
Present, sir.
Mahesh, 105.
Sir, 128 present, sir.
Right, okay. Hariprasad. Are you listening the class?
Hello?
Are you listening the class or not? Are you following the class? Okay, note on that. Calculate the loss of stress in
Sir, వినిపిస్తలేరు అంతా.
class included Vaslu. Is the problem for everyone or only for Hariprasad?
No, clear, sir, clear.
Due to elastic deformation of concrete for the following cases. For the following cases. Okay, Hariprasad. For the following cases. So we'll write on case A here. In the first one is simultaneous tensioning and anchoring of all the 3 cables. Second one, successive tensioning of the 3 cables. One at a time. So in the first case, all the wires are stretched at a time. But in the second case, one wire is stretched and anchored, another wire is stretched and anchored. So for this problem, we need to calculate what is the loss of stress due to elastic deformation. I'm just giving 30 to 1 minute time, 30 seconds to 1 minute time to just note down this question and try to understand the question. Read it yourself. What is the given data? You write down the given data. Try to maintain to write down the given data. So in this, to write down this given data, first of all, what is given? Beam width is given. Is my voice clear? Let me know once.
Yes, sir.
Yes, sir.
Okay. Now, write down the given data. I'm just scrolling up. So you people, you should tell me what are the data that is given in the question. So first one, width of the beam. B is equal to 100 mm. B is equal to 100 mm. Then what is the next? Depth of the beam. D is equal to 300 mm. So the cross-section area of each tendon. Somebody they have done, they unmuted themselves. Please mute yourself. So B is given, D is given. So you can see that the cross-section area of each cable is given. So we will note down the cross-section area of each cable only. So cross-sectional area of each cable is equal to 50 mm square. 50 mm square. పన్నెండుకి వస్తావా? పన్నెండుకి వస్తావమ్మా, కొంచెం ఒక అరగంట తర్వాత క్లాస్ నడుస్తుంది. So cross section area of each cable is 50 mm square. So in this, initial pre-stress is given. What is the initial pre-stress of the tendon? Initial pre-stress is 1200 Newton per mm square. Now you can understand what is the force, pre-stressing force in each cable. I am not calculating for all the 3 cables at a time. So pre-stressing force in each cable. So this is 1200 is a stress into area. So stress multiplied with area of the cross section of the each tendon, that will give you the pre-stressing force in each cable. Now tell me, what is this pre-stressing force?
$60,000.
60,000 newtons. That is 60 into 10 cube newtons. You can take it as 60 kilonewtons. So the pre-stressing force in each cable is equal to 60 kilonewtons. Now, coming to the next one, here area of the cross section of the beam we can calculate, which is 100 into 300. That is nothing but 3 into 10 power 4 mm square. Moment of inertia I is equal to VDQ by 12, which is 100 into 300 cube by 12. So which is what is this value? Moment of inertia. Now after calculating this moment of inertia, we need to calculate what is the stress in concrete at level of steel for each bar. So stress in concrete at level of steel. So stress in concrete at level of steel is equal, FC is equal. I am not calculating only for each cable. Just understand here. I I'm not calculating for all the 3 cables at a time. I will do one by one. FC is equal to P by A plus P into E square by I. So in this, P value is 60 into 10 cube, that is in terms of newtons I am writing down. So this is 3 into 10 power 4 plus P is 60 into 10 cube into eccentricity. What is the eccentricity? Have you checked the eccentricity here? No. Just go to the problem, just see the question. All the cables are straight and located 100 mm from the soffit of the beam. Just understand that. So the question it is given as, your beam is like this. In the cross section of the beam, your tendons, if this is neutral axis, the 3 cables, they are provided like this. And they are straight. So then if you understand this, what is the eccentricity? From the soffit of the beam, what is the distance? So substitute that 50 here. 50 square by moment of inertia. Just now here it is calculated, which is 225 into 10 power 6 single cable. I will calculate loss of stress in single cable. So write down loss of stress in one cable. Loss of stress in one cable. So that is nothing but M into FC, which is 6 into 2.67. You should ask me here, why we are doing only for one cable, why not for all the 3 cables? Why? Because this is the case of post tension, this is not for the case of pre-tension. So this will be, what is this value? The question what they are asking, simultaneously tensioning and anchoring of all the 3 cables. Write down. Under simultaneous tensioning, and anchoring of all the 3 cables, under simultaneous tensioning and anchoring of all the 3 cables, there will be no loss. But we have already said, in case of post tensioning, when all the wires are stressed at a time, then the loss of pre-stress will become 0. The loss of pre-stress will become 0 due to elastic shortening. So in that case, under simultaneous tensioning and anchoring of all the 3 cables, okay. So under simultaneous tensioning and all the wires, under simultaneous tensioning and anchoring of all the 3 cables, there will be no loss due to elastic deformation. Just remember this. If all the wires are stretched at a time and when they are anchored, then there will be no loss due to elastic deformation of concrete. Second condition, when the cables are successively tensioned, when the cables are successively tensioned. So when they are successively tensioned, so in this case, that is one by one, one over the other. What I will do is here, I will just prepare a table form. So this table form, you people need to, you also should maintain this. So just first of all understand, then you will do that one. You just understand first. So the loss of pre-stress in each cable is 16.02. Remember this value. This is 16.02. Now we need to write down what are the losses. So to calculate that, first of all, I am just preparing here these are nothing but cable number 1, cable number 2, cable number 3. So this is steps 1, 2, 3. And this is total. So I will show you how it is happening. You know the 16.02 is the stress, loss of stress in each cable. Now, first time what we are doing is you are stretching first cable. When you are doing first cable, what we said, it is successive, one by one you are doing. So initially when the first wire is stretched, there is no loss. So here the loss is 0. Here the loss is 0. Just understand here what I am writing. So the loss will be 0 when I am doing the first wire tensioning and anchoring. Whereas coming to the second step, in the second step what I am doing the second tendon stretching. In the second step I am doing second tendon. When I am doing second tendon, for the second tendon there is 0. But this second tendon, while doing this second tendon, this will create loss in the first tendon. So here the loss will be there. While doing second one, at the second tendon it will be 0, but this will create important. This is very, very important. Remember, so when the cables are successively tensioned in this, when you are doing for the first tendon for the first time, the loss is 0. But when you are doing for the second tendon, in the second tendon it is 0, but it will give to the predecessor cables. So that loss are. So how much losses will there? So first cable will experience a loss, and value is nothing but loss of pre-stress is 16.02. So that is the loss. So 16.02 is the loss in each cable. So the first cable will experience a loss of pre-stress due to elastic deformation by 16.02. Now coming to the third one. So in the third one, this is dash only here. In the third one, and why? Because at the first step you are doing only for the first tendons, 2 and 3 will not at all come into picture. When you are doing for the second one, third will not come into picture. Now when you are doing for the third one, at the third time the tendon loss will be 0 here, but this will create a loss in the previous tendons, and the value in each tendon is nothing but 16.02. That's why we didn't calculate all the values at a time. That is, here one wire is stretched or tensioned and anchored. Now in the first wire, what is the total loss of stress? So total loss of stress in each wire, first cable, if you write down all this 0 plus 16.02 plus 16.02, so this is 32.04, this is 16.02, this is 0. So the total, so now I will write down this as average loss. Average loss is nothing but total loss of all the summation. So these three things will be added by 3. So total loss by 3. So 32.04 plus 16.02 by 3, you will get it as 16.02 Newton per mm square. So this is the average loss due to, that is the loss of stress due to elastic shortening, loss of stress due to elastic shortening or elastic deformation is equal to 16.02 Newton per mm square. This is very, very important. You need to understand in case of post-tensioning, when the cables are successively tensioned, they are not tensioned simultaneously. They are tensioning is done one by one. Then they will give predecessor, the previous tendons. When you are doing for the first one, the loss is 0. But when you are doing for the second tendon, so this will create for the second one it is 0, but it will give a stress of 16.02 for the previous one. But coming to the third one, the loss in the third tendon is 0. Why? Because it is for the same third time for this third cable it is 0, but this will give a loss in the previous tendon. So here 16.02, here also 16.02. So when you add it everything, that means the loss of stress in the first cable, this is 32.02, and the loss of stress in the second cable is 16.02. The loss in the third cable is 0. You need to take off average. So summation of these three multiplied by 3, you will get it as the average loss. This is the average loss, which is the value corresponding to the loss of stress due to elastic deformation in post-tension beams. The loss of pre-stress is equal to half times of M into FC. So we know that generally M into FC will be considered as there is the loss of stress in steel due to elastic deformation. However, this is for pre-tensioning cases, and in case of post-tensioning, the average loss of pre-stress for all the tendons at a time, you are doing one by one. That means calculating in each tendon what is the stress in concrete at level of steel, then modular ratio if it is multiplied, so M into FC. So with this we calculated what is the loss of pre-stress. So in this I can do half into M is 6, that is given in the question, multiplied with FC. FC is nothing but the stress in concrete at level of steel. What is the value? Stress in concrete at level of steel?
2.67. 2.67.
2.67. So this 2.67, what I can do is, there are how many tendons are there? This is for each one. 2.67 is for each cable. But there are 3 cables are there at that level. You can multiply with 3. So you can get a stress in concrete for 3 cables is equal to 3. That means you can do like this, but in the other way, that means the loss of pre-stress, it generally half into M into FC. That is 50% of the loss of stress. M into FC, in that one half is nothing but 50%. So in any case, it says that it should not be more than 24.02 Newton per mm square. That is the condition that the caudal provision says. So that's why what is happening is, in case of post-tensioning, there is a reduction in the losses compared to pre-tensioning. That's why in the differences you will write down it as, in case of pre-tensioning the losses are more, but whereas in the case of post-tensioning the losses are less. So this is the reason how we will do that one. Last concept in this elastic shortening we will do. The next one is loss of stress due to successive tensioning of curved cables.